Okay. So, but we have to take a sidetrack to complex numbers. And this is fairly brief, but we will need this because it will save us a lot of headache. And trust me, it will make life easier. You will find online many books that do not do this leap to complex numbers. But the reason for doing this is that you don't have to remember as many complicated trigonometric identities. So one thing is, if you're integrating sine nx cosine mx, we'll be looking at integrals of this form, I think related to this. It's annoying to integrate. You can do it by integrating by parts twice. You can do other things as well by using sum and product sum identities for sine and cosine. But it's painful because you have to remember those identities, and at least I don't very comfortably think in terms of those. Another thing is that we will need to look at products of things, products of sines, products of cosines, products of Fourier series even at places. And if you have sine nx and sine mx, this doesn't have an easy expression or an obvious expression in terms of sine kx for other k. So products of sines and products of sines and cosines, they're annoying to integrate, they're annoying to differentiate, and there is a way of making these formulas a lot easier to read by introducing complex numbers. So it simplifies some formulas at the expense of, well, we have to talk about complex numbers. The reason we introduce them here is that they simplify things. And they give us more intuition, more ways of looking at things. This is one of the main reasons why complex numbers in general are introduced. And once you have them efficiently, and you don't need very much, you can do much better computations. And I don't mean just like computations by hand, I really mean by computations by computer, numerical computations. And the one thing I'll mention in this context is the fast Fourier transform. Corliss and Tuckney, I think that's their names, they rediscovered it technically. Gauss was originally the one who discovered it. In the 50s, they published an implementation of the fast Fourier transform algorithm. And that's one of the most important algorithms in any sort of data analysis nowadays. So it can be fairly said that that's one of the most important discoveries or rediscoveries of the 20th century. In fact, yeah, in computer science, it's usually included in the list of most important algorithms of the 20th century. I think one of the 7 most important algorithms of the 20th century. So if you want to do any computation, if you are doing them, you really are using things like fast Fourier transform. And to do that, you really do need complex numbers. The implementation of fast Fourier transform really is using complex numbers in some way. There are some tricks to avoid it. Of course, the calculations that the computer does are just real multiplication, but the way it's structured and coded and implemented is through complex numbers. So what is a complex number? What is all this fuss about? Well, in the simplest term, as a definition, a complex number is a pair of real numbers, x, y. So it's the space R2. When we think of it as a complex numbers instead of pairs of real numbers, we'll represent it by a math bolded C. Now, there are some things that are immediately evident from this picture. There is the length of this point, or the distance to the origin, r. So the polar coordinates, x, or one of the polar coordinates, that's square root x squared plus y squared. And then there's the theta, which is sometimes known as argument of z, which is arctan of opposite over adjacent, so y over x. This usually by convention, it depends of, often it's obtaining values between minus pi and pi, but for us, we will look at values between 0 and 2 pi, again with the understanding that it's not unique. If you have theta, then also theta plus 2 pi will be an angle for the same element. Now there's a special basis for this space, a very familiar basis, but we'll write this a little bit differently when we think of them as complex numbers. So there's the point 0, 1, which we write as I, and then there is the vector 1, 0, which we write as just 1. And with this notation, well, everything can be written as a linear combination of those two vectors. So x times 1, that's the x component, plus y times I. And we will drop the times 1 and usually abuse notation slightly and write x plus iy. This is a convention that's almost universally accepted. So it abuses notation because it obscures the fact that x is a real number, but it's understood to mean this pair xy, if really. Okay, so some notation that we need. Well, there's the complex conjugation. So here z is always x plus iy. The complex conjugate is if you flip the sign of y. This is a needed, useful operation for many things. And a picture of this, what it does is that it takes the vector z and turns it into c bar, the complement on the other side. So it flips the y-axis. Then the real part of z is just x, and it can be written using the complex conjugate as z plus z bar. So the minus cancels the 2 as z plus z bar over 2. And imaginary part is y. It can be written as z minus z bar over 2 times I, allowing for the division. We haven't yet defined that, but I'll say what it is. And we need this r, another name for it is the norm, is square root x squared plus y squared, but it can also be represented as square root z bar. An argument of z we just explained was arctangent of y over x. Now, okay, we have a space of things. We want to define a metric on it because we want to talk about convergence. And it is the usual metric. It can be written more compactly as the absolute value of z minus w. So that way it looks exactly like a real valued distance. But what it is, well, if z is x plus iy, and if w is, say, u plus ib, then it is you take the difference of the real components plus the difference squared plus the difference of the imaginary components squared. So this is the usual distance. Z is there, w is there. Z minus w would be this vector. And it's the length of that vector. So everything so far is just standard vector calculus. And with this notion of distance, you have a notion of convergence, and you can easily verify, well, this is the same metric as the product metric on R2. So if you have a pair, x and yn converging to xy, or xn plus yn I is converging to x plus iy, then this is the same thing. So if and only if xn converges to x and yn converges to y. So component-wise convergence is the same thing as convergence in the product. So this brings us back to those. Now, how do you multiply things and relate divide? Well, if you have z is equal to x plus iy, and w is equal to u plus iv, then, well, there are some basic rules that you have that you can use: commutativity, distributivity, and the crucial identity that's new, I squared is in minus 1. If you use these 3 rules, you can always evaluate the product of z and w. but sometimes, usually this is defined as this, and then these properties are verified, but it's easier to derive using those properties. So what would be z times w? Well, if you have x plus iy times u plus iv, and you FOIL this product, so you're using distributivity to FOIL, so we get xu plus ixv, and then for the second term, plus iyu plus iy times iv. Okay, what do we get out of this if we group terms? Well, we get xu, and then I squared is -1, so this is the same thing as yv. This is the real part of the product. And then the imaginary part would be, we collect the factors of I, xv, plus yu. This would be the imaginary part of the product. So this is the algebraic way of looking at multiplying two complex numbers. But there's a geometric way that is much more suggestive. I won't prove that this is true. If you have z is equal to x plus y, iy, we have the length of z, and this is called rz, and the argument of z, theta z. Then the way to represent geometrically what this multiplication is doing, well, it's taking a w with angle theta w and length, absolute value of w, and it's converting it to a vector whose length is the product of the lengths. So it's multiplying lengths by the absolute value. And it is rotating the vector. And how much does it rotate? Exactly the argument of theta. So theta z, let's see. And it's rotating clockwise, counterclockwise. So in this expression, the argument of z times w is the sum of the arguments of z and w up to a multiple of 2 pi. And the length of the vectors, or length of the product, that's the product of the lengths. So if you want to actually multiply things, it's easier to use this definition, but this is if you want to actually have pictures of how things happen. So I'll end this lecture with an example. We'll continue on these themes on Friday. Is that, okay, if we apply that rule, okay, what is the real part? Well, it's 2 times -1, so -2, times the coefficients here, 1, -1, but I squared is -1, so minus -1. And then the imaginary part would be, here we get -2i, and here we get -i, -1. And then if we compute everything and hopefully got the right signs, we're left with -1 minus 3i. This would be the product of two things. Now, a useful exercise to do, based on what we've said, is that every element, if z is non-zero, then z has an inverse, and that inverse can be given as z bar over absolute value of z squared. Now, this is defined because absolute value of z is not 0. So there's always an inverse of things that allows you to divide by things. But I'll end here. If you have any questions, feel free to stick around. There will be Friday content that will continue along these lines, and the final thing will be on Monday. I will probably review the statements that I will do on Friday, at least the most important ones, but I will not prove all of them. Those will be done just on Friday. So, thanks for joining.